Let's get started. It's really a great pleasure to introduce Professor Tamar Makin, who is the head of the plasticity lab at UCL. She started her way here at ELSC, did a stint in Oxford as a research fellow with NFPI. We'll have to forgive her for that as someone from Cambridge, and is now at UCL. And she has numerous grants, awards, but I think the most important part is that she just does really, really exciting work that I'm very eager to hear about. So,
so I realize that we'll see you guys. Thank you so much for being here. I'm so excited to be here, not just because this is where I was raised, never in this fancy building, but you know, up the street. But in particular, as I was saying, Udi, this is my very first in-person lecture in almost 2 years. This was the note I got from my university telling me we need to shut down all lab activities effective immediately. It has been a devastating almost 2 years. The lab has been shut for the greater part of a year. We're still only partially open with lots of restrictions. There's lots of studies we still couldn't get back to until today. And this has given us a huge amount of time to sit back and contemplate about what is it in research that is special to us, and what is it that we love most about science. And for me, it's always been coming up with, you know, a massively abstract and big picture type of question and trying to address it with experimental designs. So with that in mind, I wanted to share with you some work that has been done with love and with pleasure and for the sake of exploring and provoking and thinking. And I hope that with this lecture would remind you guys that we don't always have to, you know, pull our teeth and our hairs to enjoy science. Science can be playful, it can be joyful, and I hope that the presentation would convey some of that. So without further ado, I invite you to sit back, relax, and take a step into the future with me, where one day, maybe not too far from today, we may all choose to chop off our perfectly functioning upper limbs, replacing them with artificial limbs to provide us with strength, speed, dexterity, and in general, free us from the flesh and blood limitations of our own biological body. This is not entirely, sorry? You're wrong about that, but we'll talk about that later. I just want to say this is not science fiction. There are prosthetics that are available off the shelf, like the B-Bionic that you're seeing here, that in the right hands can produce incredible level of dexterity and motor control. And the question that I'd like to explore with you today is, when we design these artificial limbs for our future bodies, how much do we have to stay biomimetic? How much do we need to design close to the body? And most of the, or almost all of the artificial limbs that are being designed today, either for substitution or augmentation, like the B-Bionic that you see here, are designed to mimic the function, the control, but also the integration of the artificial limb with the body and the nerve system, as if it was a biological limb. And I'd like to explore with you today the idea, should we, could we, would we consider alternative designs with very different control principles, with very different interfaces that could potentially provide us with some of the functionality of our own body, and who knows, maybe extend and augment and provide us new opportunities to interact with our environment. So the answer to this question, like everything else, is in our brain, where we've known since the dawn of neuroscience that there exists this representation of the body in the sensory and motor cortex, with specific body parts represented separately and adjacently. And within this sensory motor homunculus, the hand benefits from some fantastic real estate. And it's not just because it's such a massive cortical slab, and not just because the hand is organized topographically, at least in somatosensory cortex, with specific sections of the hand area representing specific digits on the fingers. It's really the connectum of that hand area with the rest of the brain, with other functional areas that affords us this hand functionality that we have grown to rely on so much as humans. Now, according to the biomedical engineering community, if we could build something that approximates our body, then we could potentially plug into and take advantage from all this infrastructure that is already existing for representing our own body. And this is meant to afford more intuitive, more fluent control of the device. And there's also a hope that we'll be able to generalize from the knowledge of the motor control of our own body in order to control the artificial limb. I call this vision technological embodiment. And what I'd like to do with you today is explore the possibility of technological embodiment. So we're going to start by thinking about availability. Do we have neural resources that are available for us in order to interface with these futuristic technologies? If so, can we recycle these resources? Can we reappropriate them in order to support the control and the representation of artificial body parts? And if so, whether integrating these futuristic devices are going to impact the way our brains represents and controls our own biological limbs. So we're going to start with availability and the perhaps naive approach of the technologies that are being developed today, both for motor control and for somatosensory feedback, are to simply plug in an artificial limb instead of the biological limb. And for this, as I said, we need to design very biomimically. We need to stay very close to the body when we design. But this approach ignores foundational knowledge in neuroscience, where we know that following amputation, for example, of a digit, as shown here by Mesnick work, if you cut out one digit, digit 3 in this example, the territory that was previously assigned to digit 3 is now taken over by the cortical neighbors, digit 2 and digit 3. Similarly, from work of Pond and colleagues, deafferentation of the entire arm of a monkey leads to cortical reorganization such that the hand and arm territory can respond to inputs on the monkey's lower part of the face. So based on this and similar examples, it has been established that if you lose a body part to the sensory motor homunculus, this is going to trigger a process of reorganization or remapping. Now, this poses unexpected challenges for the biomedical engineering ambition for embodied technology. This is because if your hand area is now your face area, where and how are you going to stick an artificial limb? So we were interested in solving this paradox. And a key issue with previous literature is that in order to understand what happens in the territory of the missing hand after the hand or arm itself is lost, is by trying to understand how the representation of the cortical neighbor might change or adapt to the amputation. But this is a bit like throwing spaghetti on the wall and saying what sticks, because it's an indirect measure of what happens in this region. If you are interested in what happens to the missing hand territory in amputees, why not take advantage of the fact that amputees tell you that they can still feel the hand that is missing? We call these phantom sensations. They are notorious for being painful. They don't have to be. I'm merely talking about the experience that you can still feel the hand that is no longer there. And let me show you what happens in the brain of amputees when we ask them to move their missing hand. So here is an amputee lying in the scanner. He's moving his intact hand. This is just to show you how hand representation normally looks like in a sensory motor cortex. Now we're going to ask him to move his phantom hand. So not much is happening here in the video. But if you look in the brain, you can see that phantom hand movements elicit pretty normal looking signature of hand movement in the corresponding sensory motor cortex.
How much time after that?
So I'll get into that in a few slides, but I'll show you some striking examples. So this is from our very first study, where we used, the piece of crap fMRI we had available in 2013. And even with that crappy fMRI, we could still demonstrate that each and every amputee that we tested could activate to varying degrees the sensory motor hand area just by moving or attempting to move if they can't feel their hand so much anymore, just by trying to perform these movements with their phantom hand. Sana Kicker, the former student in my lab, has taken this a step further by trying to determine whether the topographic organization of the persistent representation is also retained after amputation. So here she's using 70 fMRI in order to elicit finger maps. This is in just random control participants. We're asking the control participants to move one finger at a time in the scanner, and we're using a phase encoding technique. Some people know it as traveling wave, in order to identify this gradient insertivity across the fingers. So here we have the central sulcus, the procentral gyrus, and the gradient here is in the selectivity, the preference to one finger movement versus the others in primary sensory cortex. So here we have the thumb, the index, the middle, the ring, and the pinky. Now I'm going to show you a map of an amputee who has been amputated, a guy for over 30 years. He has very vivid phantom sensations. So he tells us that he can perform these tasks. He can feel the 5 fingers, he can move each one at a time. And we're repeating the exact same analysis. And as you can see, central sulcus, procentral gyrus, complete map of the missing hand. Thumb, index, middle, ring, and pinky. There is less selectivity, the map is shrunk or faded, but there's definitely enough functional information for the existence of the missing hand. This guy has a high level of amputation, so he doesn't have muscles that control the hand anymore. So there seems to be fine-grained information about the missing hand despite many, many years of the hand being missing. We wanted to know whether this is something that correlates with phantom sensations or a more kind of fundamental organizing principle that once you've had a hand representation, it is there to stay. So this is a study by Dan Vesseling, another former student in the lab, and we needed to scan lots of participants. We wanted to go back to 3T. Thank God we've had Prisma by then. And what we wanted to see is whether we can tell apart representation of individual fingers. So for this purpose, we're using here representational similarity or dissimilarity analysis. So for those of you not familiar with the technique, we identified the somatosensory hand area, we ask participants to move one finger at a time. We have a pattern associated with each of the fingers, and we use Mallows distances in order to estimate how different one pattern is to the other across the finger. Just for visualization purposes, we're projecting here, this is multidimensional scaling, but we're projecting the relative distances. So each dot here is one finger for the group, thumb, index, middle, ring, pinky. The further the dots are from each other, the more distinct, the more separable the representation is. And the ellipses that you see here is really just the projected variance across the participants. And what you can see here is not only that we can make out one finger from the other, is that neighboring fingers on the hand, so index, middle, ring, for example, are represented more closely to each other, so more similar to each other in its representational space. This is important because it means that this space can capture the topographic relationship that we know is characteristic of somatosensory cortex. Yeah.
So you're talking about the activated in the somatosensory cortex.
Yeah.
What about other areas? So final motor cortex, you see it?
We do, so the beauty of S1 is that it has this very typical representation that we can capture individual participants, and I can tell you if it's there or not. The representation of the hand is less well defined in terms of the hand itself, but I can tell you that we have not found clear differences in parietal cortex. I show some high order visual cortex in a bit. We have so far not found any clear differences between the representation of the missing hand and the representation of a biological hand if you've had the hand when you're growing up. So these are control participants. This is just to show you the technique. What I'm showing you next is a group of participants that are on average 18 years since amputation. This participant couldn't be more different one to the other. They have different levels of amputation, different times since amputation, different extents of phantom pain, vividness of phantom sensations, prosthesis use, anything you can think about. But on average, as a group, you can still tell apart one finger to the other. Less so, there's less information, not significantly so, but definitely slightly less information. But the important thing for me is that the representational structure, the neighboring fingers on the hand, represented more similar to each other in the brain is still preserved. And in fact, we had 3 participants in this study that didn't have phantom sensations anymore or extremely faded phantom sensations. And we could pick up this representational structure even in those individuals. Yeah.
Is there intact hand? Is this exactly like intact controls? I mean, the same movements?
Yeah, it is if you look at the contralateral hemisphere. So if you look at the contralateral hemisphere of the intact hand of amputees, it looks the same. But when you look at the ipsilateral cortex, that's where we start seeing differences. But this is because we find lots of reorganization for the intact hand and the missing hand cortex of amputees, which is something I wasn't planning to talk about, and I can refer you to some results. But when we run the analysis, we run interactions, so we look at both hemispheres across both groups. So from this, all I wanted to take is that it seems to be a fundamental organizing principle that people that used to have a hand representation maintain their hand representation. But what we don't know from here, whether this is some kind of, yeah. Sorry? We only scanned 1 patient so far with 2 missing hands. I haven't seen the data yet. But it's an open question because I'm not sure if the intact hand is not contributing to the maintenance of this presentation somehow. So what we don't know from these results is whether this representation that we find here is some kind of residual property of the network, or whether it really maintains the unique life experience of the individual participants. In other words, whether this is the representation of a hand or their hand. Okay. So to answer this, Hunter Schoen at Carson has been running the world's most difficult study, I'm pretty sure, of people that are about to undergo amputation. So here we're working with a patient that suffers from a slowly progressing tumor in her arm. So by the time she needs to undergo amputation, she sustained quite a bit of nerve damage to her both nerve and muscle, meaning she can't really do our individuated finger movement very well. So here we're looking at her healthy hand, the unhealthy hand, a couple of days before the amputation, and this is 3 Tesla lunatic ball maps. And what you can see is that for the healthy hand, we get a decent map, thumb index, middle ring, pinky. For the unhealthy hand, we can still make up thumb index, middle ring, pinky, and pretty stable representation from one scan to the other. But it's a lot more messy than I like to see in these maps. It's a bit disorganized, and I can't tell if it's disorganized because she's been disabled for about 10 years before the amputation, or maybe she can't perform the movements very well. What I can tell you is this is her unique hand representation. Okay. Now, what happens after the amputation? So here we're scanning her 3 and 6 months after the amputation. And as you can see here, the messy map, qualitatively looks pretty much the same 6 months after amputation relative to pre-amputation. So it seems to us, based on this study, and this is still ongoing, but it seems to us that this phantom presentation that we find here really captures the unique fingerprint of each individual participant, really stores the knowledge and the information, which potentially validates this maybe naive notion of embodied technology. But before I move on, I want to have a quick digression, because when I present this, normally someone in the audience, I was counting on Elon, would ask, what about Mersnick, right? Mersnick, the reorganization story, right? Mersnick, the guy who showed that if you amputate one finger, the other finger is going. So it's hard, these studies are incredibly difficult with people that are about to become amputation, for the sad result that most of them don't make it and die before they get to their post. It's a very extreme procedure to do. But what we can do, and again going back to 7 Tesla, is use a model for amputation, which is local nerve block. So we anesthetize a finger just for a couple of hours. It's not, it's not a great amputation model, but we can take away the input for a couple of hours, and we can see if we can replicate Mersnick's results. Okay. So here's the experiment. We construct this finger map for each participant, and then we scan them one time without a nerve block and another time with a finger nerve block, so that we don't have input from digit 2. So this is just unthresholded winner takes all map, so the same as Makin was doing within the hand area. So this would be 3A, this would be 2, so 3B, 1 here. And what you see here with the color code is boxes that show selectivity. Or not even selectivity, just a preference to one finger compared to the others. And if you see the white line here, this is from our independent localizer. So this is just kind of for us an estimation of where we should find high selectivity for the two. Now this is the map we get after the block. So we repeat the same analysis, this time for 4 fingers. So four fingers winner takes all. And this is the area where we expect to find high selectivity for the finger that we anesthetize. And as you can see very beautifully, half of this area is taken over by B1 and the other half by B3. So very nice replication of the Mesnick result. This is an example participant. Here we have the statistics showing that this is an independent localizer, so we don't get it 100% of the time, but we're counting the number of boxes here that show selectivity for digit 2. It's most of them, and after the amputation, which is a nerve block, the majority of boxes respond to the cortical measures. Yeah. Sorry?
Do you get the signal?
So we don't get signal for D2 because we blocked it.
Yes and
No, so we used resting states to verify this. This is the bold response, and we didn't find any differences in the fluctuations. We ran MR spectroscopy to look at the change in the concentration levels, and we find I think an unexpected increase in GABA levels. But MRS is, not the best technique in the world. Yeah.
But the once experiment that you cited was up to several years.
Yes.
And that with time, the persistence increases, so that following many years after you would expect it to the opposite direction.
So they don't show. So Horns was kind of 2 shots. So they did, sorry, 1 shot. So we just waited. There was a whole story about the monkeys being held up. So I think it was 10 or 12 years. And just 1 shot and looking at it. So they didn't follow the same monkey. There was one study which was carried out by Mesnick with median nerve, where they were looking at monkeys kind of more over time. And the map is from day 0. The map is dramatically changed from day 0. And then there's kind of retuning of the receptive field sizes. They become smaller and they become more organized over the next few weeks. But within 2 months or so, you're pretty much very close to the final map.
What you're saying here is that the most of the fact that what you see very shortly afterwards.
All I'm saying, I didn't finish the slide. All I want to show you is that if you want to see Mesnick, I can replicate Mesnick. But maybe let me go one more step to show you why I'm showing you this. Like, sorry, you had a question.
Baseline and only record the short fingers.
This is exactly what I want to show you. So when you do this analysis, it's apples and oranges. It doesn't make sense. Here you're doing 4 alternative fourth choice, because presumably you're amputated, and you're doing 5 alternative fourth choice. Of course, the maps, by definition, the maps are going to look different. It's a silly analysis. So what if we do exactly what Ilan suggested? Yeah? I'm sorry. So we go back to our baseline map, and we really do the same analysis. We get the exact same map. It's not surprising, I think. The whole concept, the whole principle of topographic representation is that the cortical neighbors would share representation. So I don't find this particularly surprising. We can quantify this. You see that the baseline map, if you just take the 4 fingers, looks very similar to the final map. And maybe more interesting, and this is something I won't get into today, but please read the paper, which I very hope will be accepted in the few coming months. When we look at the block maps, we can actually make up D2 even though there's no activity in D2. And this, I think, is driven by the same principle. There's actually a lot more overlap in the representation of the fingers than ascribed to us in the textbooks. Meaning you can make that, you can complete the missing parts by the other fingers. But this is just, to show you that we need to be a bit careful with how we interpret or accept these drawings that we get from the textbooks about remapping, because there's a lot more that needs to be added underneath these selectivity maps. So this concludes my availability part, and if you guys are on board, we can move on and ask, now that we know that there are available resources, can we actually recycle them or reappropriate them in order to use an amputation link? Yeah.
Not on board yet.
Okay.
So I don't understand, how do you summarize this report?
I want to say that there are resources available after amputation. You don't have to worry about remapping or reorganization too much.
Information about the amputed parts of the body
Is maintained.
still there in the
Yeah.
That's where you have to, that's the starting point. But did you demonstrated it in the functional in the MRI studies, but I'm not convinced about the reinterpretation of nerve results.
There's lots of ways to
It's
reinterpret
not
memory.
just that when this is not active, there was another activity there. It's that there was an amputation, and there was a long time after that
Definitely.
where other functions took.
I'm not saying remapping doesn't exist. I'm saying remapping is only one aspect of a very complex process that is
But you are very
happening.
careful. Here in this room, you can be more broad.
This is
Tell us.
recorded, so you're not going to get more. You're not going to get more than me. This is recorded.
I don't know what the other aspects are.
But in case of pawns,
Yeah.
it was across centimeters, right? The reorganization, the remapping was not something minimal. But
We have done so.
extended across the.
We have done, again, I don't have the slides, but we've done multiple studies in humans looking at the face. Most recently, we've actually taken a huge effort to map out different body parts, because in human amputees, all the research is on the lips and the chin, but this is not the cortical neighbor of the hands. The cortical neighbor of the hands is the forehead. So we said, okay, we can't get it for the lower face. What about the upper face? And again, we're using representational similarity analysis, which is wonderful because it gives me information about the information content. And it's really important because nothing changes in terms of information content in the deprived cortex. And the changes that we see in activity are sometimes due to just changes in inhibition and masking, but don't necessarily change the functional property of the area. They could be to do with homeostatic toxicity, just maintaining or stabilizing the activity, but don't necessarily produce information. And everything we've done, and we've done many studies with amputees, we cannot find any evidence in acquired amputees of the face going into the hand area. So I know you all love pawns, but I cannot, for the life of me, replicate it in humans. I can replicate it like that in individual subjects if I'm looking at people that were born without a hand. They have incredible
difference.
No, because acquired amputees don't have it. Congenital one-handed people that were born without a hand do have it. So it's a staging development thing. It's not a species thing. I don't want anyone to replicate the PON study because it's a horrible study, but I kind of do. I kind of want to see replication.
What about imagined motion in people who are
Yeah.
not amputated?
So we've actually done imagined in the first study that I showed you of the finger maps in the 7 Tesla, and the maps disappear when you ask them to imagine, both amputees and controls. When you ask an amputee to imagine moving their phantom hand, you don't get these maps. It's only when you ask them to try and move their hands. And this is because the only way to activate these areas through movement, if you have a high level of amputation or nerve damage, is through the motor system. And what we think is driving these maps that we can identify here is actually the efference copy from the motor system, rather than the input from the periphery.
If the difference copy was the source for this representation, would you expect to find similar maps also in the Tamar?
Yeah, definitely. So these are just selectivity maps, so it can only pick up areas that show stronger response to one finger compared to the other fingers. But if I just ask for activity, you find the entire sensory motor system. So you find premotor cortex, cerebellum, parietal cortex, SMA, the works. So it's just the way we do the analysis looking for this high level of selectivity. Yeah.
So therapeutically, it's wonderful, but I'm sure you're aware of Hilary Putnam's Brain in the Butt.
I do.
So according to him, when the brain in the butt says, I see a tree, he's not seeing the tree.
Yeah.
And it's best illustrated with an octopus.
Mm-hmm.
The tactic is in the arm, but the strategy is in the central. So how would you, unless there is...
This is brains in a vat. Having a representation of the hand that you don't have is equivalent to being a brain in a vat, because you don't have that body part, but you have that representation.
But you have to have the experience of
Yes.
living, and then the afterlife.
Exactly.
Like
Exactly.
heaven.
Yeah. All right. How are we doing with time? Because I have two more pieces, and I don't want to. All right. All right. Let me try this on you. This is as cookie as the no, actually there's got no. We're gonna get cookier as we go along. Sorry. All right. I'll just continue and see how we do with timing. So can we take advantage of brain resources that are available to represent our own body in order to represent a body part that is artificial, that we didn't have before? So there's different levels to answer this question, and in particular the important kind of semantics here is, what do we mean by embodiment? What do we mean by representing an artificial body part as we represent our own body? But just one quick example I'm going to go through relates to how we represent the body in the brain in terms of activity and decoding. So this is a study we have run with Tanya Orlov, who is sitting somewhere here. Tanya and I have shown quite a while ago, together with Udi, that not only sensory motor cortex has this topographical representation of the body, we can also find it in occipitotemporal cortex. And specifically, there are areas that show increased selectivity when we show people pictures, images of upper limbs in comparison to other body part or object categories. So in this study, we're interested in understanding how prostheses are represented in this area. So we are showing participants images of hands and objects, and this is just to identify for each participant these hand-loving areas. And we also show participants images of artificial limbs, either cosmetic prosthetics or functional prosthetics. The cosmetic prosthetics are specifically designed to mimic the aesthetics of a hand, so they really look like hands, but they're not operable. And the functional prosthetics are prosthetics that are designed to substitute hand function, but are typically not looking like hands. And for most of our participants, they wear these hook-like devices that don't look anything like a hand. And our question was, what happens in these hand-loving areas? And we're showing people images of these folks. So if we just look at net activity levels, we find the desired result, which is that prosthesis users can engage more these hand-selective areas when they're viewing images of prosthetics compared to control participants. So they're able to engage these hand areas when viewing prosthetics. But does that mean that they're actually representing the prosthesis like a hand? To answer this question, we go back to representation of dissimilarity analysis. This is a study by Ronnie Moore and other former students in the lab, where we use this technique in order to determine how similar or distinct the representation is of these cosmetic prosthesis categories or functional prosthesis categories to the native categories in this area, which is hands and toes. So here is what we find in controls. So then the Lincoln trees shows how similar the representation is across two patterns. So here you can see that the cosmetic prosthesis category is represented very similarly to hands in control participants. And I should say these are participants that are family members and friends and people who work with amputees. They're used to seeing prosthesis being used, but it doesn't really matter for them. The hand-looking prosthesis is represented like a hand, a real hand, whereas the functional prosthesis are quite distinct from hands and instead represented a lot more similar to tools. Unsurprising, uninteresting. What about prosthesis users? So here we have 32 prosthesis users, which are either congenital or acquired amputees. And what we find for them is that both the cosmetic prosthesis and the functional prosthesis are not represented at all like a biological hand. They're also not really represented like tools. Instead, we find this convergence that cosmetic prosthesis are represented more like functional prosthesis and vice versa. We can quantify this kind of emergence of this prosthesis category away from the two native categories. Oops, sorry. Hold on. This is this prosthesis category index. So the higher the value, the more distinct the representation of prosthesis categorically than the other two categories. So what we find is that people that use their prosthesis more in daily life, have better prosthesis users, they are the ones that end up representing the prosthesis less like a hand and less like a tool and more like a prosthesis. Okay? So the fact that we're relying on resources that were maybe originally devoted to representing hands doesn't mean that the brain is going to represent the prosthesis like the biological categories that are there. We were very anxious to replicate these non-intuitive but interesting results. We ran out of amputees in London. So instead, my student, shown, ended up working with litter pickers. These are the Londoners that clean our streets, and they use this very generic tool for multiple hours a day. And we wanted to know whether the litter pickers would represent their expert tool more like a hand, or like the amputees, less like a hand, okay? So here we're showing them videos of various objects in various settings being lifted either by a hand, by a litter picker, or here we use the control handheld tool, which is arms here. We have a group of novices and a group of experts, which are the litter pickers. And these are the similarity matrices. So each little square that you see here would compare two videos or the responses in the brain, these visual and selected areas, between a video of the litter picker category and the hand category. And the more yellow the color is, the more distinct the information is, the greater the parallel distances are. And as you can see here, the experts, the litter pickers, show more yellow here in this critical comparison between hands and expert tools. In other words, they're representing the expert tool less like a hand, more differently from a hand. Sorry?
But they also do it for the
Yes. So here we actually find a generalization for the other handheld tool. There could be various reasons why, and we elaborate on that in the paper. But the important point for me here is that using a tool a lot doesn't make it embodied, doesn't make the brain relate to it more like a hand.
Sure, tools. Here, the Tom's got a similar purpose as litter. So it's a bit hard to say what would have a similar purpose to hand, but maybe tools that have a similar purpose to the prosthetics would be represented more similar.
So in the prosthesis study, we didn't find selectivity to the prosthesis types that people use. So if you remember, we showed them pictures of cosmetic prosthesis and functional prosthesis, and we actually also showed them pictures of their own prosthesis that they use. And the effect was also generalized. So we also find the same happening regardless of the specific type of prosthesis. And when we had those results back there, we thought, well, in the lifetime of an amputee, they would experience through multiple prosthetics, and they have to replace them every few years, and they normally have more than one. So they have a primary one and a secondary one, depending if you're going to the gym or you're going to a wedding, you wear different prosthetics, right? So we thought this is because they have enough experience and are able to generate a lot of prosthetics. But this result tells us that there may be some semantic links that would allow to generalize from the example that you have experience with to other related examples. We don't know yet, but we believe this is probably semantic in both cases. Any more questions on this? Okay, so to summarize so far, there are available resources that are dedicated to represented our hands that are maintained despite amputation. And we are potentially able, I've shown you an example in visual cortex, but other groups are of course working on some other sensory and motor system. There are available opportunities to take advantage and plug into these areas in order to extract relevant information. But the fallacy that we tend to have here is that if we take the information from these hand areas, that means that this brain area is going to decode or represent or control the artificial body part the same way it would the biological body. But at least naturally, at least when you just let amputees use these artificial, this is not the case. The brain is smarter and can come up with maybe more suitable models in order to better reflect and represent what it is that this device is for the brain in terms of motor control or semantic content. And one thing I can tell you, it is not a biological hand. An artificial limb, as sophisticated as it is today, is not a biological hand. And the brain can tell the difference. This opens up potential opportunities for us to think outside of the box of biomimicry. So it gives us permission to try and think about alternative ways we can create artificial body parts that don't adhere to the biological template of the body. And the last question I'd like to explore with you is how these slightly more bizarre devices would impact the representation of our own biological body. Here I have the great pleasure to introduce you to, the third sound designed by the wonderfully talented Danny Flood, which I'm very proud to have as a member in my lab. Danny designed this third sound in order to allow able-bodied people to achieve more with their already fully functioning hands.
So,
yeah.
So does the extra artificial limb take some part of the brain that cannot be used for other purposes?
Let me show you what I have so far, and then I can tell you what I have and I haven't shown you, and then you can. So the thumb is controlled with pressure sensors that we place underneath the big toes. With one, you would flex and extend, with the other, adapt and adapt. So it basically gives you a full range of movement as a biological thumb, so that you have your right thumb and your left thumb on the same hand. And this poses interesting questions for motor control, starting with how do you control a body part that you never had before? And what's going to happen to your own biological body representation in order to afford the representation of this extra body part? So, Polina Chialiva, former student in the lab, has taken up the first challenge, which was for us most important, make sure that when we're playing around with these technologies, we're not impacting too much people's own body representation. So she ran a 5-day training study where she's training people to use the extra robotic thumb. And this included both in the lab training, but also outside the lab. And before and after the 5 days of training, there'll be an extensive battery of behavioral tests and MRI. And she also had a control group that had to wear the thumb for the same amount of time and go through the same amount of training, but they couldn't operate the thumb because we took out the battery. These are examples of some of the tests we were doing in the lab in order to collaborate between the hand and the thumb. So here you see, for example, what we call a collaboration test, where you have to do something with the hand and the fingers of the hand together. So with the thumb and the fingers of the hand. Here you see what we call a shared supervision, so splitting attention to two different things. And here we have an individuation task, so really focusing on the thumb alone, and for this we're occupying the problem. So on average, people were using the thumb for about 4.5 hours a day, half of it outside the lab. So they were really, finding out ways to take advantage of the thumb in the daily routine. This is my favorite training task. This is the coordination task. So you have to move the thumb in order to find the tips on each and every one of the fingers in structured order. I love this task because it takes 2 degrees of freedom and because it is something that people can do pretty much immediately. So it's a very intuitive task.
So just say one word, what is the control mechanism?
So you have pressure sensors, which we place underneath the toes. And then there's a Bluetooth signals to a servo, which would rotate the thumb in 2 degrees of freedom. The engine is placed here. You have a battery pack, everything is wireless. You have a battery pack here, and the servo is linked to the thumb here, so that it can move into rotating 2 degrees of freedom.
Using the toes was the
Using the
ideal.
This was, so Dani came to me with this. This was her master's project, the thumb. And this was, she's the designer, she comes from product design, and this is what made sense to her. Since then, we've been experimenting a lot, especially with lots of anesthetics and other ways of trying to understand what is unique about the toes and how the representation of the toes can be coordinated so well with the movements of the hand. We've been playing around a bit with Dario Farina, so looking at EMG, so trying to extract information from the arm, but everything else seems to interfere with the ability to fluently move, whereas there's something very intuitive about controlling your feet together with your hands. There's so many, you know, from driving to playing electric guitar to playing piano. I mean, many designers have realized that there's something very intuitive about combining foot movements with hand movements. But we are running, I mean, I'm showing you one study, we are running a lot more studies with this wonderful creation. And again, Dani is incredibly talented. So this is just showing you how people improve number of hits and how many fingers they can find over the 5 days, and people of course get better. So they start with some ability, but they get better over days. What is more interesting for me is that before and after the 5 days of training, we've asked participants to perform, the task blindfolded, which is something they haven't trained on. All the use of the thumb is always with direct vision. And people were fantastically good at controlling the thumb in this coordination test while being blindfolded. So to me, it means they're really developing a sense of proprioception of the position of the thumb relative to the position of the biological finger, which is for me quite extraordinary. This is our other training tasks. You wouldn't be surprised to learn that practice makes perfect. It's true. What was more interesting for us is that on one of the collaboration tasks, the genital building, we've actually given participants in the 1st and 5th day a dual task, a cognitive load task. So while they're building their building, they also have to run through some very simple arithmetical calculation. And this is to increase the cognitive load so that they have to take some attention away from what they're doing with the hand. And we were surprised to find that not only in the late stages of learning, but also in early stages of learning, the cognitive load task didn't impair performance, meaning they are able to perform these tasks with a good level of automaticity. So again, this is a very intuitive device. People know how to use it. I'll skip this one and get maybe to, for me, the most important part of this study, which is given that people can learn to use the thumb intuitively, develop good amount of motor control with it, proprioception, and some experiential embodiment, which I won't go into, how is that going to impact their own use of their own biological hands. So if you've noticed when I showed you the training tasks, people were wearing gloves. These are data gloves. They allow us to track the kinematics of the hand while participants are wearing it. And what we see here is a very simple principal component analysis of the movements participants are making two groups during these daily tasks that they have to perform. And what we find here is that, to explain the same level of cumulative variance, the augmented group requires slightly higher number of PCs. In other words, the hand movements are slightly more complex, where they are integrating the thumb, incorporating it into their tasks, compared to just moving your hands to perform the same tasks. And we can unpack this with using this interdigital movement coupling matrix. So it simply shows us how much we tend to co-move fingers together. This is the control group. This is very classical co-movement matrix. It shows us that digits 3, 4, 5 are quite closely coupled. When we manipulate objects, we tend to move these 3 fingers together, whereas digit 1 and digit 2 are relatively independent. This is the augmented matrix. The effects are very minor, which is why I'm just showing you the difference, so it's easier to visualize, and this is the summary. We see that relative to the control, the augmented group tends to individuate digits 3, 4, and 5 slightly more, ever so slightly more. What it means that in order to expand the motor repertoire, in order to take advantage of using the thumb, they are breaking their natural synergy. And this is simply because they're using these fingers together with the thumb, okay? So they're breaking a habitual way of moving the hands that we think is motor control is very meaningful. Yeah.
It matters where the thumb is. So if the thumb rather coming from the other couple, different.
It might change the specific pattern here because you would maybe use a different combination of fingers. But what doesn't matter is that any augmentation device that you would build, and no matter if it's like an antenna coming from your hand, if it's designed to extend your motor abilities, it's going to invite you to change the way you do things with your own hands. Otherwise, it wouldn't be an augmentation device, it would be a tool. So inherently, something has to give, something has to change in order to take advantage of these devices, I believe. Okay. So given that people are using this thumb for, 4.5 hours a day and changing the way they're using their hand compared to how we normally would, how would that impact the brain? And this is the last result slide. So just bear with me for like 1 more minute and we'll be done. And we'll do really well by the way. So here again, we're looking at the hand area. Now we're going to look at the primary motor cortex rather than the somatosensory cortex. And you're already used to these representational similarity projections. So thumb, index, middle, and pinky. This is the left non-augmented hand. This is the right augmented hand. These are the baseline scans that we take prior to training. And there's not much to see here except that the data is great. We can get very high level of separability. Now, I'm going to wash out this baseline for you so you can see what happens after. It's a small effect, so look carefully. But what we find is that following amputation, in the left hand, not much changes. So this is the non-augmented hand, the cream is washed out, and the first is the colored one. But for the right hand, we have a very minor but very consistent shift in the representation of the fingers away from baseline and towards each other. So we can quantify that by just looking at the distances, the overall distances across the fingers. And what we find is a very, very small but consistent reduction in the similarity across the fingers. So there's a very mild collapsing in the representational structure of the hand. We have time for one more slide. I just want to convince you that this is not an interesting plasticity effect. So we also look at the relationship between the feet and the hand. We can't do that in primary motor cortex because the body part representation is too segregated. So here we're looking at SMA, which is the premotor area. And the critical difference here is between the representation of the hand and the toes, so nothing much is happening in the left hand. In the right hand, as you've seen for primary motor cortex, we see this very small shift in the representation, but there's a greater similarity now between the hand and the feet, which results in a significant fraction. But luckily for us, we also had a control body part here, which is the mouth. And we should change for the mouth. We're not using the mouth differently because they had an extra finger. And we find a similar effect for the mouth. And for me, this is important because it tells us that this collapsing, this mild collapsing that we see is not organized, or at least probably not to heavy plasticity, at least not after 5 days. And we think fits much better description of homeostatic plasticity. And there's some, if you're interested, we ran some simulations in order to show this idea in the paper. Yeah.
What about the control group that had an extra finger but couldn't move it because
We couldn't move it because.
there was no battery? This is one of the controls.
Yeah, so
Change.
yeah, so we did not find significant differences between pre and post in that group, and that's also in the paper. But we did scan as well. So it's not the increased usage of the hand. All right, so just to wrap up, I think if you'd like to design for the future body, my advice for you is stay close to the body, but not too close. On one hand, there are built-in resources available in the nerve system that are uniquely designed to afford motor control, to integrate relevant sensory information, and to increase learning. And we have a bunch of studies now showing that all of these can be harnessed, for example, to control an extra body part that you've never had before. But this doesn't mean that you have to stay biomimetic or stay close to the body when you are coming up with these devices. There are other features, both in the brain, but also in the 3D design that could be utilized to support or replace or even extend our biological bodies. And I hope that our research will inspire the biomedical engineering community to try to think a bit more outside of the box. And I think this is a message that we have been learning as humans time and time again, where rather than kind of trying to mimic a model of how something is operated, if we can instead abstract the principles and design for the principles rather than the shape of what this is, we not only can achieve the function, but we can also exploit it for new uses that God didn't intend when they created the original design. With that in mind, I just want to thank my fantastic lab and Danny Cloud in particular. And this is it. If you don't have questions, I want to tell you there's a paper that was just out today in bioRxiv. I wanted to put a slide and I couldn't, about the gender gap in editorial activities in an editors-led journal, which is eLife. And I encourage all of you to take a look at it and maybe have a think about how this gender imbalance might reflect or project on you individually.